In this lecture, we're going to examine the titration of a weak acid with a strong base. This is different from titrations you may have performed in an Introduction to Chemistry course where you titrated a strong acid, like hydrochloric acid, with a strong base. Today, we're going to look at the differences when we titrate a weak acid with a strong base. And the weak acid we'll choose is acetic acid, CH3COOH. It's located in the beaker below the burette, and its concentration is 0.300 molar. We'll titrate this weak acid solution with a strong base, sodium hydroxide. Its concentration is 0.250 molar. And we'll monitor the pH of the resulting solution with every increment of sodium hydroxide with a pH probe. This pH probe will read out a pH and will record the pH with every sodium hydroxide addition. We'll take this information then and put it on a graph called a titration curve. And this titration curve is a plot of pH versus the volume of sodium hydroxide that we incrementally add. The graph has on its y-axis the pH as read out by the pH probe, and on the x-axis the milliliters of sodium hydroxide that we've added to get to that specific pH. Not surprisingly, the pH of a weak acid like acetic acid should be relatively low to begin with. After all, it is an acid, and this is indeed the case. The pH starts out very low for the acetic acid all by itself, but as we add sodium hydroxide, you'll notice that the pH does go up. This makes perfect sense because the pH of sodium hydroxide is very high, and the only direction that sodium hydroxide can move the pH is towards larger and larger pHs. And so we should not be surprised that the pH would go up with every addition of sodium hydroxide. However, in this region, the pH does go up. It doesn't go up very quickly. That changes, though, later in the titration, where the pH begins to dramatically change, moving towards very high pHs very quickly, and then where it begins to, again, plateau. This curve, called the titration curve, is one that you should be very familiar with. Now, we're going to identify specific and important points of this curve, and where we're going to focus our attention first is on the region in red. We're going to use our eye to determine an approximate midpoint in this region in red, the place halfway through the plateau, as I'll refer to it. Now note that the dot that I've put in that halfway position doesn't necessarily coincide with a data point. I'm using my eye to estimate the best position now for that midpoint. This midpoint is known as the half equivalence point, or the pKa point. It's an important point that we will discuss in more detail later. However, what is important is that you recognize that at this point, the number of moles of weak acid, that is the acetic acid, is exactly equal to the number of moles of the weak base. That would be acetate. Note that this is acetate, not sodium hydroxide. You see, as the acetic acid is being neutralized by the sodium hydroxide, acetate ions are being produced, and the half equivalence point is reached when exactly half of the weak acid has been neutralized to produce an equivalent number of moles of the weak base, acetate. In any case, we will get back to this point a little later. What is important, though, is the number that corresponds to this point on the pH scale. This number is known as the pKa value and has certain important aspects or uses that we'll get into a little bit later. But for the moment, what we're going to do is identify the pKa point on the pH scale, and then we're going to imagine moving from that pH up 1 unit and drawing a line, and also moving down 1 unit and drawing a line, and using those two +1 and -1 marks to establish a region which is called the buffering region. Now, the buffering region is a region, first off, that has relatively constant pH. As you can see, the pH doesn't change much as we continuously add sodium hydroxide. The buffering region is also identified as a region where the pH is relatively constant. Buffers attempt to maintain constant pHs, and this buffering region would be the operational region of a buffer if this is what we were trying to construct. All right, so the buffering region, and halfway through the buffering region is the half equivalence point. Now, the next thing we're going to do is we're going to identify this type of problem as a type 1 type of problem, there are three different weak acid, strong base types of problems that I'll expect you to know how to perform. And in this type 1 type of problem, the idea will be for you to be able to calculate or determine the pH in this buffering region. That is, before we reach the equivalence point, something we have yet to talk about. In examples to come, we'll look at the details involved in determining the pH of a solution as that solution is operating within the buffering region, and this will be known as a type 1 type of problem. All right, now next up we're going to look at a different region. You'll see that I've drawn a couple of extra horizontal lines in there, and my goal here is to identify a point halfway up the rather steep slope that immediately follows the buffering region. All right, a ruler and is really all you need to do this. There are tools that you can use in Excel to help you with this as well. But in this lecture, I'm just going to go ahead and identify that midpoint with another point on the graph. Now, this doesn't coincide to a data point either, but it does identify a point halfway up this rather steep slope, and this point is known as the equivalence point. The equivalence point is often what you are seeking when you're doing a standard strong acid, strong base titration. You're looking for the equivalence point, and the reason is because at the equivalence point, the moles of the weak acid that you had to begin with will be equal to the moles of the strong base that you've added. Now, this isn't like the half equivalence point. The moles of base in this case we're talking about are the moles of the strong base, sodium hydroxide. Frequently in problems involving a strong acid, strong base titration, you'll use this idea and information about the number of milliliters and the concentration of NaOH that you've used to determine the moles of the NaOH, and thus, because it's equal to the weak acid, or the strong acid I should say, the moles of the strong acid. In this case, though, just note that the number of moles of weak acid are equal to the number of moles of strong base. All right, this type of problem is known as a type 2 type of problem, and you'll be asked to perform calculations where you'll determine the pH at this point, at the equivalence point. The machinery that we use is slightly different from that which we use for type 1, and we'll have examples of that yet to come. Now, to wrap all of this up, we also have the remaining region, those data points that we acquire, the pHs for which we've added enough sodium hydroxide that we have now gone past the equivalence point, and we would want to be able to determine the pH for these points as well, and these constitute a type 3 pH determination, probably the simplest of the three types of problems to work through, as it doesn't require any kind of equilibrium treatment. In any case, we'll look at examples of how one determines the pH in a type 3 problem as well.